Hello everyone, thank you very much to attend my presentation. I am Lucélio da Costa from Electrical Engineer Department of Coimbra Polytechnic. Today, I will talk about a technical economic analysis of a power supply system for electrical vehicle charging station using photovoltaic energy and electrical energy storage system. The outline of my presentation is presented with a short introduction. I also present the methodology used in my work, theoretical background, case of study, simulation and optimization of my study, and some discussion, and finally conclusion. How we know the world's demand for energy is increasing rapidly, putting a great strain on existing energy resource and having a negative impact on the environment and global warming. As governments strive for a green energy economy, electric vehicles are playing an increasingly important role in helping to reduce emissions from the transport sector. Electrification on the transport sector is an important step towards a sustainable society. We know the foreseen massive deployment of EVs is driving the solution to the challenge of combating climate change and urban pollution, with the aim of providing a balanced and sustainable response. Nowadays, using an EV to get around the city center is one way to reduce urban pollution and to contribute to the sustainability of the planet. We know as well the sales of electric cars have increased significantly over the last 10 years, and an important question arises: what to do with EV batteries after they reach the end of their life? So, this work aims to investigate the possibility of incorporating another fast semi-fast charger into an existing system without having to increase the power contract with the public grid. For this, it is to investigate the technical and the economic feasibility of installing a PV system and battery storage system, comparing the reusing lithium batteries or new lithium battery for different case studies. The methodology presented in my work is the software homogrid, that means hybrid optimization model for electric renewables. The software homogrid is a very robust optimization model developed by National Renewable Energy Laboratory that can be used to simulate different power system configuration or mixes of components, optimize design options for cost efficiency, or perform sensitivity analysis based on inputs of loads, components, and recharge. This software can combine PV system, different type of loads like EV charging station, battery, grid, and so on, as we will see next. Here we have a system modeled on the homogrid software. How we can see, we have a bidirectional converter, we have a grid, we have our load, that is EV charger. We have two types of battery system. Here we have a new battery, and here we have a reused battery from Tesla. In theoretical background, we can see the power output of the system here, okay, and we have the PV array configuration here, and the PV modules where NES is the number of modules connected in series, and NP is the number of strings connected in parallel. And finally, PMSTC is the output power of the PV modules and the standard test condition. This figure can show us the solar global horizontal irradiation on the city of Coimbra. As we can see, it is a city with a lot of solar energy potential. We can note that it is possible to produce solar energy throughout the year, but mostly in summer months like June, July, and August. Now we will see the grid connection. The electrical vehicle charging station and investigation is connected to the public power grid. The software between the electric vehicle charging station and the grid is made in lower voltage with 400 volts with 3-phase, 75 kilowatt connection. In Portugal, the price of energy varies throughout the day, the month, and the year. This figure shows a variation of energy price over the year by color band. For example, here, in the hard color band means that energy price varies between 0.07 and 0.14 euros per kilowatt hour. Here we have the load profile. This is the daily energy profile modeled in Homer grid. This profile is based on 1 month data from the electric vehicle here charging station Coimbra. The average daily energy is equivalent of 320 kilowatt-hour, and by extension, this value was considered for the remaining month. This is the location of the real EV charging station Coimbra, Portugal. The charging station has a 15 kilowatt charger of the Portuguese company, SESC. This charger has 3 different sockets, namely the CCS2, CHAdeMO, and MENEC sockets, but can only charge 1 vehicle at a time. We analyzed in detail the charging events of August 2020 of this real EV charging station Coimbra, and we noticed that several occasions were detected where there was at least 1 EV waiting for the charger to be freed, to be able to charge, so at least 1 more charger would be needed. However, the connection to the network has limitation, and it is not possible to charge more than 1 electric vehicle. Therefore, in order to expand the system and thus increase the availability of service without increasing the contract power to the grid, other solutions would have to be considered, such as energy storage and PV system. This is the proposed scenarios that will allow a simultaneous charging of 2 electrical vehicles. Here we can see we consider 2 charger output power, and with the meantime connection 0.6. It's mean 37 minutes, and 2 charger, and scaled average 15. The second table, we have the characteristics of the electric vehicle visited charging station in Coimbra. Based on 2 types of generic EVs were modeled, taking August of 2020 as a reference. We have a generic EV to correspond 76% of EV population visiting the charging station, and we have generic EV2 correspond to 24%. Both have different energy requirements. The first one required 50 kWh and can be charged with the power of up to 26 kW, while the second one requires 24 kWh and can be charged with a power of up to 50 kW. For better illustration, we can see here the new annual energy profile based on the proposed scenarios modeled in the home grid software. In this figure, we can note the vertical bar here on the right side represents the charging power of the electrical vehicle in kilowatt, where the warm color orange, red represent the higher power, okay, in this place, and the colder one, I mean blue and black here, represent the lower power. But what does it mean? This means that several EVs can be charged at the same time, as the warmest color range corresponds to the power range between 17 kW and 100 kW. This table gives us the cheapest case, and the one in which the EV is charged with the help of PV system, storage system with Tesla reused battery, bidirectional converter, and finally the grid. This is the same result of the previous table, but here we can see it more clear. The winning first case simulated in home grid is PV, energy storage system with second life battery from Tesla, converter, and the grid. The winning second case simulated in home, we have PV, energy storage system with a new battery and converter and the grid. The third one is only considered PV, convert, and grid. The last case is only the grid. As we know, this is the base case that doesn't allow us to cover more than 2 EVs. Here we can see in this table the comparison between the base case and the winning case. These are some economic results of our winning system. Here the net present cost is the main economic output of Homer software. How we all cost, and we can see here the lower cost system compared to the base case. How we can see the cost we incur over the lifetime of the project with proposed scenarios is much lower here, is much lower than the base case. Now, let's move to the discussion section. Initial capital of a winning system equal to approximately 13,000 euro and with a return on investment of 70%, with the internal rate of return 22%, and the investment were covered from the 4.2 year. We have annual saving of this system approximately of 7,000 per year. The second winning case used the new lithium battery. This solution is less economically viable than the first case, that we can see here the initial capital of 34,000, and we have the return on investment in 30.4% and the internal rate and 18.3%, and we have in this second win case the simple payback of 4.8 years. The third win case we consider PV, inverter, and grid. This result is the initial capital reduction of approximately 13,000 euros. And here we have a 26% of the return on investment, and we have an internal rate of return approximately 13.4%. And here obviously we have the reduction of payback 3.27 years. The fourth winning system is currently installed. This system cannot meet the load when two EVs want to charge at 15 kilowatts at the same time. Here we have some conclusion. This work shows that the photovoltaic energy generation system and the battery storage system can cover most of the needs of charging stations of EVs connected to the grid. Despite of limitation of the software home grid, that which does not allow to create our own strategy when we can define when to charge the battery from the grid or not, it provides to be very powerful to analyze the economic viability of the system. If proper care is taken as pointed out, namely checking the current available models and prices of the considered component. It was also showed that a system consisting of a storage system with a second life batteries can be advantage over new batteries because of the latter's high cost. This study also suggests that the use of PV and storage system is possible to increase the available power beyond the contract power. And I would like to thank to the Prior Energy for the partnership in this project. I would like to thank to the Portuguese National Funds to support this work. Thank you very much to your attendance.